Okay, perfect. So hello everyone and welcome to our CGDG meeting. And today we have Renzo Bonifazi from Wageningen University, and it's the Division of Animal Breeding and Genomics you're from, right? Yeah. And he is working on international genetic and genomic beef cattle evaluations and is giving us an insight into his latest work today. And so if you have questions for Renzo, just write them down in the chat, and I'm going to read them after the talk. Or we are also happy for you to unmute yourself and after the talk and ask the question personally. And yeah.
Okay, thank you very much, and welcome everyone. And thanks also for the opportunity to show today our research. The research I'm going to talk about is basically a wrap up around my PhD program, my PhD thesis that is coming to an end in May next year. So actually it was quite beneficial also for me to try to tell a coherent story in 40 minutes of the different research we have done here in Wageningen. So before I start, I want to thank my supervisors and co-authors, Jeremy, Jan, Rul, and Mario. And next to them, I want to thank all the people involved in this project. You will see we need to pull data between different countries. This requires a lot of organization. So I want to thank ICAR, Interbeef, and Interbeef for providing the resources for the PhD and also for providing the data and the infrastructure. Next to them, I also want to thank the other advisors and all the national organizations, in particular those you see here at the bottom of the slide. And because they provided the genotype data, so it's quite sensible information for research. So I'm really happy and grateful for that. So the outline of today's talk is going to be first a bit about interbeef evaluations. So what are they? And this is the main framework where I place my PhD thesis. Then I'm going to show you 4 different studies, different stage of development from published and under writing or work in progress. The first 2 studies are about genetic correlations. The first is about estimating correlations using multi-trait approach. The second is a specific type of investigation on direct maternal genetic correlations and their impact on breeding values. The third is on how to use genomic data in interbeef using single-step approach. And the fourth study is work in progress on how to integrate the international breeding values back into the national evaluations. So talking about international evaluations, why do we need them? Well, during the last century and keep going nowadays, we have a lot of reproduction technologies development, and we have access to top genetic materials of elite sires from different countries. And since we have exchanged genetic material, our populations became much more connected than before. So our populations in cattle are connected across different countries. If you think about Holstein Friesian breeds in dairy, then you have the perfect example of connectedness. And all the breeders, and especially the importers and exporters of frozen semen, seek to compare the top sires at the domestic level with top sires from foreign countries. So for this reason, Interbeef first for dairy cattle and Interbeef later for beef cattle were founded. The main role of these 2 organizations is to help breeders to select the top genetics from other countries and help breeders to better achieve their selection goals. So here you have the classic example of why we need these organizations. Let's imagine we have 2 countries, UK and Spain. Each country ranked their 3 top bulls based on a breeding value for a specific trait. And let's say now we are in Spain and we try to import the genetic from UK. We try to import the top bull from UK. Most likely this top bull won't perform exactly the same in Spain. And the reason for this no consistent ranking of breeding values is the existence of a genotype by environment interaction, or in this case, genotype by country interaction. In short, G by E is basically tell us that the genotype of an animal won't perform exactly the same in 2 different environments. So to help national organizations, the international ones deliver an international breeding value that is expressed on the scale of each country. That means you can compare your domestic sires with the breeding value of foreign sires. So this international breeding value that is delivered back to the countries has been computed using data coming from national organizations. To do that, we need to exchange from the country point of view to the international organizations 2 types of data. the pedigree data because we need to connect them. And second, we can exchange phenotypes and or genotypes. Either this can be raw phenotypes and genotypes or proxy of them when we have some limitation, for instance, due to privacy. Here I report the example of the usage of the regress proofs, which is an approximation of the phenotypes. So this really depends on the type of evaluations we are looking at and the type of service and breed. So what is the current situation in Interbeef? Currently, we have 15 countries involved in the evaluations. We have 2 traits evaluated per year, winning weight and calving traits. Calving traits are composed by calving ease and birth weight. And we have soon coming up carcass traits composed by weight, conformation, and fat. And we have fertility traits under research, and they're coming up soon as well. We have 5 breeds evaluated twice per year. And you can see also in this map which countries are participating. So maybe you can see if your country is in this map. So this is the framework in Interbeef and the exchange of data that's going on in Interbeef evaluations. And this is where I place my research. So I want to explain first how this works. Let's imagine we have 2 countries, country A and B. Each country performed their national evaluations using pedigree and phenotypic information. Eventually, they may also have genomic data at the national level, and they run their national evaluation and get their national breeding value and their national reliability. The same goes for country B. Then when we participate in international evaluations for beef, countries send their pedigree and their raw phenotype to Interbeef. In Interbeef, we run a pedigree-based evaluation with a model called the Amasi model, and I'm going to explain this next. Out of this evaluation, we get out an international breeding value and an associated reliability, which should be more accurate as we did not only consider the data from country A, but we also consider all the data of relatives recorded in another country. These breeding values are then distributed back to the countries, and it's up to the country to decide how to use them in the national evaluation. So these are, again, the 4 studies, and I'm going to show you where they allocate. So the first 2 are about estimation and impact of genetic correlation. So they are key parameters that we plug into the model. So this is where they allocate. And then the 3rd study is about improving the existing pedigree-based model to include genomic data with a single-step approach. And the 4th study is about the distribution and the integration of these breeding values back into the national evaluations. So as I'm going to use the same model across different studies, I thought, okay, let's explain this now. We have our current model is called the Amasi model, stands for Animal Model Accounting for Cross-Country Interactions. This model is fully equivalent to a multiple trait animal model, where you basically fit the countries as different correlated traits. And by doing that, we model each trait or each country phenotypes using the national model. So we fit all the underlying national fixed and random, both environmental and genetic effects. So as most of the traits, actually all the traits we have at the moment are maternally affected traits, this will be an expression valid for modeling any phenotype we have. We have Y, the vector of observations. So for example, winning weight, then we have B and R, vector of fixed and random environmental effects. U and M are direct genetic and maternal genetic effect of the dam. P is the permanent environment from the dam, and E is the residual. All these random effects are uncorrelated between countries, with the exception of the direct maternal genetic one. Indeed, for these 2 genetic effects, we model across countries genetic correlations. And it's thanks to these correlations that we can account for genotype by environment interaction. When this correlation is smaller than 1 between 2 countries, then we may observe re-ranking of breeding values. So maternally affected traits are specific type of traits, let's say, that are very frequent in beef. So I thought to explain a bit further how the genetic correlations between countries look like when we have maternal affected traits. Let's imagine we have a sire that is made of 2 cows in 2 different countries, and each cow starts to have 3 offspring each from that sire. So we know that the phenotype we are going to record is going to be affected by the maternal abilities of the mother, so of the dam. And maternal abilities are, for example, milk production and maternal cares. And maternal abilities create similarities within the same families and variation between families. And we need to remove this effect from the observed phenotype when we model them. So next to the genetic effect, we also dissect the maternal abilities into components, a genetic one and a permanent environmental one, which is common to every offspring of this cow. And then, of course, we have the residuals. So the genetic of the dam is of interest for beef breeders because we can actually select for heifers that have good maternal abilities so that we can have offspring with better weights at weaning, for example. So if you consider this at the country level and you plug these vectors eventually in the mixed models, then you have to model the genetic correlations between the two countries. And this is how the two populations of two countries will be modeled in terms of genetic variances and covariances. This is a symmetric matrix, and on the diagonal you have the variances, and off the diagonal the covariances or correlations if you convert that to correlation matrix. So here you can see that you have three partitions. You have the direct partition where you have direct variances and direct covariances between the countries. You have the maternal partition, which basically model the variances and covariances for maternal breeding values. And here you have the direct maternal partition. This partition can be further divided in two parts: the RDM or direct maternal covariances within the same country. So this basically model the covariance between the direct effect and the maternal of the same country. And in the off diagonal, you have the modeling of the covariance between the direct effect in one country and the maternal in another country. So this is what we are trying to research in the first two studies in my PhD thesis. So the first study is going to be about how to use a multi-trait approach to estimate these correlations when you have a lot of countries. So to estimate these correlations, what we need actually is to have in place genetic connections between countries. These connections come from sires, just as in the example I just showed you. So these sires have to have recorded offspring in 2 or more countries, and they're also called common bulls. However, in beef, we have a problem, structural problem in the data. Usually we have a structural low genetic connectedness, and that's because we have lower usage of artificial insemination compared to dairy cattle. So the connectedness level usually is quite low or medium, or at least not comparable with dairy breeds. Further, we have these maternal genetic effects that makes the estimation even more challenging, because we don't only need these bulls to have recorded offspring, but we also need them to have recorded grand offspring in 2 or more countries. So in this framework, the estimation procedure is quite challenging, and we have the method in place at the moment is that we estimate 2 countries at a time. So we run a bivariate model, and we use a sire maternal grandsire methodology model. That's mainly due to limitations on the software and the data amount and number of equations we can handle in reasonable time. However, doing with this the estimation using this bivariate model, and not only we can see some estimation, some challenges related to the estimation of correlations. We have issues with convergence, and some parameters are really difficult to estimate. And when this happens and maybe they go out of parameter space, then we need to default the correlations to a starting value to start our international evaluation. So we thought, can we do better? And one thing that we wanted to do was, instead of estimating correlations 2 countries at a time, is to estimate them all at a time. As you can think, by looking at 2 countries at a time, we are basically breaking down some of the connections. If you think of a sire that connects all the countries together, then it will be beneficial to use a multi-trait model, so all countries together, and therefore not breaking down these connections. So this was indeed the aim of this study. We wanted to estimate across country genetic correlations using multi-trait approach. And also, once we have done that, we wanted to understand how we can subset the data and how these subsets will influence the estimated correlations. So to do that, we have available winning weight data, maternal affected traits, therefore, for limousine breed and across 8 populations. Here you can see a summary of the data and the 8 populations. These codes are quite easy to recognize. The only one you may not be familiar with is DFS, stands for Denmark, Finland, and Sweden. These 3 countries joined together as a single country in international evaluations. In total, we had a large data set with more than 3 million phenotypes, but you can see it's quite unbalanced, with majority of the phenotypes coming from France. And that will become important later. So these data were recorded in a long period of time, more than 45 years of records. So the first thing we usually do is to try to understand how much connectedness there is in a data. So the challenge here is that we are dealing with large data set, and therefore we need to use straightforward measure of connectedness between countries. Here in this table, you can see on the diagonal the number of sires that have offspring in each country. and in the lower diagonal, the number of common bulls. So these sires that have recorded offspring between two countries. So for example, there are 65 common bulls between DFS, Denmark, Finland, Sweden, and Czech Republic. It's not only, as you can see here, you can notice there are no missing connections. So all pairwise countries are connected with some common bulls, but there is quite some variation. We go from 44 between Spain and Czech Republic up to 10 times more between France and Great Britain. But it's not only important how many bulls we have, it's also important how many offspring we have from each bull. So another measure usually we compute to understand how connected is the data between two populations is this genetic similarity coefficient, and is computed between two populations at a time. It is basically the proportion of number of offspring coming from common bulls over the total number of offspring coming from all bulls using the two countries. And you can see the results in this upper triangular part. And here, what you see is that we define 3 arbitrary thresholds based a bit on literature studies. There is low genetic connectedness if GS is below 0.05, if it's between 0.05 and 0.10 is medium connectedness, and above 0.10 is high. And you can see from the color coding that actually the situation is not that bad. Besides some combinations with Great Britain, we have a medium level of connectedness, and it stands out that Ireland and France mainly have the best connections with other countries. This actually makes sense because most of the data come from France, and these data are from a French breed. So what we did was to estimate genetic correlations using all countries together and using all data together. This is a quite large data set, and the way we could do that is using Mix99 software, where we have the variance component estimation implementation in that, which use this MCEM-REMOL. It's an algorithm that allows us to handle large amount of data at the expense only in computation time. So once we estimated that these correlations using all the data, then we implemented other scenarios where we subset the data and try to improve computation time. And to do that, we found that a straightforward methodology is to select the hairs. And we focus on the French population because it's the biggest, and reducing small populations will not really improve computation time. Also, France is the most connected population, so it is important we do that carefully. And here we implemented 3 different scenarios. The first scenario was to randomly select the hairs, and we did 3 analyses like this. I'm going to show you the results of the average of these three random samples. Then we computed the genetic similarity, so the same formula I showed you before, but at the hair level. So this formula now is telling, this coefficient is now telling us how much an hair is connected to another country, and we rank and select the most connected hairs. Finally, we implemented a similar scenario, but we extended this formula to include also the information on common maternal grandsire. So as I said before, for maternally affected traits, we thought it could be beneficial to consider also the information coming from not only bulls, but also not only bulls with recorded offspring, but also with recorded grand offspring between 2 countries. So now I'm going to show you how usually a matrix look like in this context. It's a lot of parameters. Here is the matrix with the 120 correlations estimated using the whole data. Without focusing on the numbers, basically here you have the 8 countries, and you can see the same partitions that I showed you before with an example of 2 countries. You have the direct correlations in this block, the maternal one in this block, and here you have the direct maternal correlations, which can be differentiated with the diagonal ones being within countries, and the off-diagonals are the between countries ones. So the values you see in blue are those that previously were not estimated or had convergence issues, so were defaulted to arbitrary values. Here we were able to estimate them, and we thought that therefore this was quite a nice result, that we didn't have convergence issue when using all data together. So next to that, now I'm going to summarize each block with a box plot, and then I'm going to show you how these correlations will change when you implement data subsettings. So here you can see the correlations for direct block and for maternal block, and you can see a box plot of them. And here you can see on the x-axis the different scenarios, and the value on the x-axis is actually the average. So there was an average of 0.79 for genetic correlations direct, and the maternal ones were on average 0.71 when using all data. Then when we remove the data, so we start to subset the data, we can see that for direct genetic correlations, these were quite consistent across different scenarios implemented. And also you can see that they don't change that much for the direct effect. For the maternal genetic correlations, actually, they change a bit more, about 0.05 less compared to using old data. The biggest impact was on these direct maternal genetic correlations. So in short, these are called RDM in this presentation. They can be divided in within countries. Here we have 8 countries, so we have 8 of them. And between countries, we have 56 of them. On average, they were minus 0.12 when using all data and 0 for the between countries RDM. And when we subset the data, this is how they change. You can see that now they become more negative, with on average about 0.24 or 25, depending on the scenario, for the within countries RDM. And also we see that they become more negative when we reduce the data, also the between countries RDM. Also here, we can see that there is no much difference between subsetting scenarios. So the conclusions of the study was that we have now the possibility to estimate genetic correlations using multi-trait approach, but this goes to the expense of computation time if we don't apply any subsetting strategy. Therefore, the quickest and maybe easier way is to select most connected hairs. And if we selected about 500,000 records, we aim to about 2 weeks computation time, which should be feasible within calendars that we have in Interbeef and our deadlines. We also didn't see any sensible differences in the scenario we suggest. There is a small difference for direct and maternal genetic correlations, and the biggest difference relates to this RDM. I will point you to the paper if you want to know more. It was published last year in GSE. And here you will find much more details on connectedness between countries and also an extra scenario we implemented based on the harmonic mean, which focus more on how to select balanced data between different hairs. But the main message here is that also in this scenario, it didn't really matter. So I left it out for matter of briefness. Knowing that the biggest impact was for this RDM, we thought to follow up and understand more on this specific type of correlations. So this is the second paper we have worked on. And well, as I said before, at the national level, you have to model the within countries RDM, and these are usually small and negative, and are provided by the countries. At the international level, however, you have the between countries RDM, and we don't know much about them. And they are usually difficult to estimate. And the current procedure is that we just fix them to 0. So we saw that when we use all the data, actually from the previous study, they were on average 0. So this would support this, this assumption of fixing them to 0. There was some variation around it, but on average they were 0. However, when we look at France, which has a lot of data, almost this RDM, almost all these RDM between countries are negative. So we thought, okay, maybe this assumption is not that safe if you consider that France provides a lot of data. A negative RDM, which will be assumed to be 0, may affect our breeding values. So what we wanted to answer here was is there an impact of ignoring, and therefore set to 0, this between countries RDM on Interbeef breeding value? So in the example before, this will be like doing so. Instead of modeling these covariances, we just fix them to 0. Is there any impact? So to do and answer this research question, what we did was to use the same data as before and implementing 2 scenarios here. The reference scenario model exactly the correlation of the big matrix I showed you before, the all data matrix. So we model all RDM, both within countries and between countries. And then we have the current scenario. This is supposed to mimic what happened in the current evaluations, where we fix to 0 this RDM between countries. Then we compute and compare breeding values using rank correlations between the 2 scenarios for different group of animals. And here I'm going to show you 3 main results. The rank correlations for all animals, animals grouped by their reliabilities, and for publishable sizes. When this rank correlation was above 0.99, we assumed there was no re-ranking. If these rank correlations were between 0.98 and 99, there was small re-ranking. And if it was below 0.98, then we assumed there was large re-ranking. So here we go now into the results. Our model is an animal model. So you get out a vector of breeding value for all animals in the pedigree. And since it's multiple trait, you get this vector of 3.4 million breeding values in each country scale. So here we are looking at the rank correlations of these breeding values under the 2 scenarios. And here you see on the x-axis the different countries, and the rank correlations are on the y-axis. You see here for both direct and maternal breeding values. So for direct breeding values, as you can see, the rank correlations are well above 0.99. So it seems that ignoring this RDM between countries and fix them to 0, it doesn't really matter on breeding values re-ranking. It won't happen. But on the maternal breeding values, you can see that actually there seems to be an impact, either small or large, with rank correlations even below 0.98. So we want to further investigate this. And what we did for the maternal effect now, I'm going to show you the groups of, we basically group animals by their individual reliabilities. So we define 3 classes of reliabilities associated with these breeding values under the model reference. And here I include both male and females. And you can see here the rank correlations for these 3 classes. Animals were grouped for reliabilities below or equal 0.3, between 0.3 and 0.6, and above 0.6. So the darker the color, the higher the reliability. And if you look at this figure, you can see a general trend where you see that the higher the reliability, the higher the rank correlation, signaling that when we ignore this direct with this RDM between countries and we fix them to 0, if the breeding value has a good reliability, actually won't really matter. But as soon as the reliability drops below 0.3, then there may be an impact. So actually, you don't get back this whole vector of breeding values, but one major category of interest of Interbeef evaluation is for publishable sires. What are publishable sires? These are top bulls that pass specific rules we have in Interbeef based on the reliability associated with their breeding values, the number of progeny and grand progeny recorded across different countries, and that you can include in your booklets or in your magazines. So in this dataset, we had more than 32,000 direct breeding values and 13,000 maternal breeding values that we could distribute back to each country. So we look at this particular category of animals because these are of particular interest for breeders. And we saw that no matter which country and no matter which effect, this category is quite stable, and ignoring RDM between countries didn't affect the re-ranking of these breeding values. We ultimately think that the rules we have in place are restrictive enough to make sure that this assumption is quite safe. So the conclusions of this study was that ignoring between countries RDM caused no re-ranking or small re-ranking for maternal breeding values, limited especially to animals with reliability below or equal to 0.3. We didn't see any re-ranking on publishable sires, and therefore here the results support what happens in reality, that we could fix to 0 this RDM between countries, quite difficult to estimate. But of course, this RDM should be close to 0 on average, as we saw in this previous study. I will point you to this paper, which was recently published in Journal of Animal Science. And here you will find much more details that are left out for briefness. And for example, we also implement a new scenario where we fix also the within countries RDM to 0. And the main message is that this will cause re-ranking also for publishable sires. You will also see different group of animals defined, and quite some discussion on what will happen if this RDM will actually be different from 0. Okay, so now for the second part of the talk. Now we go into the model, and we are trying to include genomic information using single-step in beef cattle. So why do we want to use genomics? Well, there can be different reasons. Maybe the most straightforward is that we want to increase the accuracy of breeding values using genomic data. But we know that genomic predictions accuracy depends on size and setup of the reference population. And we also know that with single step, that is nowadays much more used in both dairy and beef, we can exploit the 3 sources of information at once, and we better achieve this goal. But implementing national genomic prediction can be quite challenging, especially if you have small populations. And if you have very small population, then it can even be not cost effective. So either way, if we are looking to expand your reference population through international collaboration or to join together small populations, then it can be beneficial to have an international genomic evaluation. Examples already exist. Here I report some of them. We have the genomic maize service from Holstein breed, intergenomics for both brown Swiss and Holstein. These 2 services come from Interbull Center. Then you have also other projects, international projects, where you have, like here I report the example of GDMI and Gentor. These projects collect difficult to measure traits, therefore quite expensive, and it's beneficial to put them together, to put the data together, because you quickly reach a sizable reference population in less time. So what is the situation in beef at the moment? Well, as I showed you before, countries may already have national genomic evaluations in place, but most of them right now are collecting data. So what you see is that there is an increase in genotyping rates, while at the international level, we do use the raw phenotypes, but we don't have yet genomic data. So the question here is, how can we include genomic data? Well, an optimal scenario would be that countries send to Interbeef their genotypes so that we can run a single-step approach and use these three sources of information in an optimal way without any approximation. And when I say here genotypes shared, I don't mean the genotypes are shared between countries, but they're only sent for the international evaluation. So this is quite an important point to stress, that countries don't get access to genotypes. They get access to a genomic breeding value computed using the three sources of information. So the aim of this study was, one, to develop this single-step evaluation, and two, we wanted to understand if there was any impact on bias and also any benefit on the accuracy of including this genomic data, both on top of the current international evaluation and also compared to the national ones. So to answer this question, we put in place different scenarios that differ on two levels. First, if they include only national data, and here we are therefore including only nationally submitted phenotypes and genotypes, and also international if we include all data together. Then the evaluations could be pedigree-based, so no genomic, or single-step if we include genomic. For the genetic evaluations, we use the same model I showed you before, and for the genomic, we implement genomic information using single-step SNPBLUP on top of the current model, following Liu and colleagues. And we also fit two J factors, one for the direct effect and one for the maternal effect. And these J factors help to make pedigree and genomic information more compatible for the single-step approach. So here you see the four different scenarios implemented in MixBLUP, a software we have here in Wageningen. And you see we have the pedigree national evaluation, the single-step national, the pedigree international scenario, so the current model, and the new single-step SNPBLUP international. So we computed the estimates of level and dispersion bias using the linear regression method of each of these four scenarios. And knowing their expectation for unbiasedness, then we can compare and rank the scenarios. Then I'm also going to show you, for understanding if there is any benefit, the increase in population accuracy of moving towards single-step SNPBLUP from any other model. So this will be like doing so. From any other model, we move towards single-step, and we get an estimate of the increase in population accuracy. The population accuracy is defined as the correlation between the true and known breeding value and estimated breeding value, and is of course an estimate. And here you can see that, for instance, we have the comparison which we were really interested in understanding what is the benefit compared to the current pedigree evaluations. The validation group in this validation part is composed by young animals born in the last generation with both genotypes and phenotypes. So here we have a new set of data. I don't know if I can put this. I don't know if this is in the middle. Okay. We have a new set of data, still limousine breed for winning weights. We have 5 different countries participating in this study with more than 300,000 phenotypes. And we had genotypes available for more than 17,000 animals at a genotype of at least 42K or higher density. We imputed these genotypes to a selected panel of SNP using FindUp, and after quality control, we were left with about 58,000 markers. So this is the distribution of genotypes between countries. You can see that after quality control, we end up still with more than 17,000 genotypes. And you can see that it's actually quite unbalanced. Most of the genotypes come from Ireland, followed by Switzerland, Czech Republic, and then Germany. No genotypes come from the FS, but still we included everything in a single step. The amount of genotypes with phenotype associated for winning weight was on average 60%, with some variation depending on the country. So now into the results of this study. Here you can see results for level and dispersion bias. And you will see a color coding common across slides. So the red bars are for pedigree-based models, blue for single-step models. Then you have the national scenarios are full lines, and the international ones are strip lines. And here you see the results for level bias expressing genetic standard deviation for direct and maternal breeding values. Of the 4 countries, we could define the validation group as composed by phenotypes and genotypes. So you don't see the effects because we don't have genotypes. An unbiased evaluation will yield a level bias of 0, this green line on the y-axis. And here you see that we have some negative level bias across all countries. And a single-step model seems to give better estimates, but actually, yeah, not that much improvement. And for the international models, we see that we are following what happened at the national level. For maternal breeding values, we have some variation depending on the country and the model, but we have either positive or small positive or small negative level bias. For dispersion bias, an unbiased evaluation will yield dispersion value of 1. We consider acceptable, similarly to the interval validation test, values between 0.85 and 1.15. And nonetheless, here you can see that for direct breeding values, most of the countries had over-dispersed breeding values. And beside Ireland, yeah, they were all over-dispersed. And a single step also here seems to improve a bit, but some of these differences were not significant. And you can see here that the international models, again, seems to follow what happened at the national level. For maternal breeding values, they were all within the range of acceptance, but for Germany, they were still over-dispersed. So we think that this picture, negative level bias, over-dispersion, it could be explained by selective genotyping. And that's also because when we rerun this validation using animals, young animals, so last generation with phenotypes only, then the estimates of level and dispersion bias get closer to the unbiased value of 0 and 1 respectively. Now into the benefits of using this genomic data. And here I'm going to show you the increases in accuracy relative to each starting model when you move towards single step. So for instance, if we take Czech Republic under PBLUP national, there is an increase of 9% of the accuracy you will get under PBLUP national when you move towards single step international. You can see that for regardless of the country or the model, we still have positive increases. And for direct effect, we have positive increase, similar positive increase between national and international PBLUP models. And also for countries like Ireland, there is a benefit when we move from single step national to single step international, signaling that there is still benefit of pulling together genotypes also for these countries. And you can also see that maternal breeding values seems to have more increase compared to the direct, but if you think about it, this group is a group of young animals, so they should have smaller accuracy to start with. So it's easier to increase a smaller accuracy for this type of, for this breeding value compared to the accuracy that you will get under direct breeding values. So the conclusions of this study was that we develop a single step genomic evaluation for beef using a SNPBLUP approach. And we evaluated and observed similar level and dispersion bias compared to the current pedigree-based model. And it seems that this international bias seems to follow what happened at the national level. There is benefit in pulling together genomic data with this single step approach. Either we see increases compared to national models, pedigree or genomic, but also compared to current pedigree evaluations we have in place. These increases were on average 14% for direct breeding values and 26% for maternal breeding values across countries. Actually, we can expect higher increases because we know that countries are collecting genotype at a good phase. And also, if we add more countries joining, actually, we can expect even higher increases. So this work is in preparation. So hopefully you will see some preprint out soon. So now, last 5 minutes, I wanted to talk about the work I'm currently doing. It's a work in progress, and it's about the integration of these computed breeding values back into the national level. And yeah, as I said before, Interbeef is going to distribute back these international breeding values. You are going to get back these breeding values, at least for your national animals, plus this group of publishable sires I showed you before. Many countries, however, still publish 2 breeding values, one national and one international. Why? Because sometimes we don't have a procedure to join together these 2 sources of information, and they can differ. These differences are actually quite easy to understand. If you think about a national evaluation, it includes data from most likely different traits, some of which we don't have in Interbeef, while the international evaluation don't do that, but includes data from other countries. So these breeding values can be different. And this disagreement is actually, I think, creating we think is creating quite some issues. So another disadvantage of not doing anything, but just using the international breeding value as it is that you don't get any propagation of this information from animals recorded in other countries into your national data. If you think about using crossbreed data, for instance, or if you have 6 months of new data at the national level, then offspring of these publishable sires don't get any benefit from the international evaluation breeding values. So what we are trying to do here is that we are trying to use an integration methodology to integrate the international, either traditional or genomic breeding values back into the national evaluations. What we aim to do is that with this methodology is that you can take the international breeding value and use it with your up-to-date national data. And then you get out one single breeding value where you blend the two sources of information. Here there are two challenges. One is that you need to avoid double counting of national information, and I have a quick slide on that. And also there are some approximation steps of this procedure, so we need to understand if it performs well or not. So to study this, we have on top of the data I showed you before, new data from Limousin, from Italy, from the Anacli Association. Here we have more than 100,000 winning weights, and we have no genotypes at the national level. So here we put ourselves from a country point of view, and we try to implement real case scenario. Here we are integrating these international breeding values into Anacli evaluations, thinking of being with having extra data at the national level. This happened because Anacli makes 4 evaluations per year. Interbeef does 2 evaluations per year. So there are 2 evaluations where Anacli has more data than it happened to have sent to Interbeef. So here we have the 3 scenarios implemented. We run international evaluations for beef with data up to January 2019. Then we run the national one with national data only up to May 2019, so 4 months extra data. And then we have the blended evaluation where we integrate the first into the second. And what we are trying to do here is to evaluate first the accuracy of these steps of this integration that I'm going to show you. And also we are trying to understand if there is any benefit. And what we aim to achieve is an increasing predictability of our evaluations, or what is predictability is basically the ability to predict the new breeding value that these animals are going to have as soon as we add more data with time. So here we have the integration procedure is 5 steps. It's quite full, so I'm going just to guide you through the slide. It's actually not that, I don't want to confuse you, but basically you have the same, in this panel, the same steps I show you at the very beginning of this presentation. You have Italy with their national evaluations on this side, and then you have other countries here with their evaluations. The difference is that other countries have genotypes and Italy doesn't have genotypes at the moment. So what you do, you first run your national evaluation and you get your national breeding values and reliabilities, and you also run the international one, either pedigree or genomic, and you get your international genomic or pedigree breeding values and the reliabilities. So far nothing new, if not for the new genomic model. Then the integration part basically consists on converting these breeding values and reliabilities in an associated measure, which is a pseudo phenotype called DRP or direct regress proofs, and an associated weight or measure of how many information was this phenotype associated with. And these are called ERC, that stands for effective records contribution. You can convert that for both international and national evaluations. And once you do that, then you need to discount and avoid the double counting of national information, computing DRP adjusted and ERC adjusted, using this formula that comes from Jeremy's thesis. So why do we need to avoid double counting? This is quite easy to see from this figure. That's because we use national data once through the national evaluations, this way. And the second time we have used it by sending them to the international evaluation. So these national data are now accounted another time in the international breeding value. So once you have discounted the national and avoid double counting of national data, then you can take the data you have now 4 months ahead up to May 2019 and include the DRP adjusted and ERC adjusted pseudo phenotypes and run the blended evaluations. In this way, you get only one breeding value where you not only used the new data from Interbeef, but you also have propagated that information to the young animals at the national level. So as I say, this is work in progress. I don't have results yet, but I thought to show this. Basically, here what you see is these publishable sires, and you can see here the differences in reliabilities for this category of sires and foreign sires. That means sires that have no offspring recorded in Italy and that are publishable in Italy. Here you see that the reliabilities for single step are greater than pedigree-BLUP international models. And here you see in these plots, the reliability national on the x-axis and the international in the y-axis. Here computed using pedigree models, here computed using single step. And of course, under pedigree models, there is no much difference if an animal is genotype or not. But if you use single step, you can see clearly two groups here. And therefore, here the question is, does the integration procedure work? Will the integration procedure work well for both GABV and EBV? So this is what we are trying to answer also. So this is work in progress, and I hope to present it as the next in the next conferences. And yeah, talking about conferences, I want to leave a message about WC Gulp, which is coming to the Netherlands next year in July. Paper submission is open since September. So if you have something interesting, please consider to submit it. We also have a session on beef cattle chaired by Martino Cassandro, Fernando Cardoso, and myself. So if you have nice research on beef cattle, please consider to submit a paper. And yeah, thanks for your attention. And I will leave here some contacts and will be happy to take questions or suggestions.
Yeah. Thank you very much, Renzo, for this really, really interesting talk. I've already seen one question from Georgios, but so yeah, if you have questions, just I don't know whether this is Zoom, whether you can anyway, just write it down in the chat or unmute yourself. But we start with the question from Georgios. So he's asking, or he's saying that rank correlations are quite sensitive even to minimal re-ranking. How much genetic gain would be lost if rank correlation drops from 0.99 to 0.98?
That's yeah, that's a good question. Yeah, so in the paper we do a bit more than just rank correlations. So we also look at the consistency using the LR method, but we didn't really look at the genetic gain. Yeah, this of course will require that you look at yeah, changes in the genetic gain. I think it can be investigated by looking, for instance, at genetic trends across years. And yeah, I plot that, and there was no much genetic, no much difference. But yeah, the issue with genetic gains and the plotting of genetic trends is that yeah, we don't have that much information to judge them and decide how many selection paths there has been, and so it's quite challenging to define to look at genetic trends. I think this will require a close lookup with country members. Yeah.
Okay, thank you. Georges, if you want to follow up on this, you can just unmute yourself, or
no, it's fine. Thank you for the response, Renzo.
okay.
Thank you.
Thank you. So there are no questions so far in the chat. So I have one more general. I don't know whether this makes sense or not. It's regarding the first part of your talk, where you presented the different scenarios or subsets to increase computational time and simplify the analysis itself, or the estimation of the breeding values. So my thought was that countries are quite artificial constructs, and some countries are more similar than others, and some countries have higher, or you described higher genetic correlations between some countries compared to others. Would it be an idea to summarize the similar countries or group the similar countries together and have therefore less numbers of comparisons? Yeah,
indeed, that's actually a good point, because indeed that's what I think it happened with DFS. Denmark, Finland, these three countries decided to join together, and the genetic correlation between these three countries is not different from one. Therefore, they don't expect to have differences between countries we're ranking. And yeah, in that way, basically, you reduce the number of traits in the model. But an issue associated to that is that then you need to have maybe a common model for the different countries. So, and we see that models are actually similar but never the same. So you always have different effects, or maybe the contemporary group is modeled as random instead of fixed, or you have a permanent environment in the model, and maybe there is one country that doesn't have it. So then the harmonization of the trait also come in place. And but definitely, sure. I mean, this model is easy. The model is easy to understand. It's quite also following what happened at the national level, right? Because you fit the national model into the international one. But if you are going to have 40 or 50 countries like in dairy, then of course you have a lot of correlations to estimate in one go.
Yeah.
And the strategies of one of the strategies that they try in dairy, and that's why we try the multi-trait approach, is that when you estimate genetic correlations, always try to include one country that have a lot of connectedness. So for instance, in Holstein, they try to always include the US or Canada, where they have a lot of connection, less next to countries where you don't have that many connections. And this seems to be beneficial.
Okay, this would have been my follow-up question, because we've done some not similar work, but we estimated breeding values across countries for dogs, for German Shepherd dogs. And what we found is that the phenotypes, the way the phenotypes were measured, were very different between the countries. So they use different systems and so on. How standardized is it for?
Yeah, so for winning weight,
Yeah.
it's actually
For example, yeah.
For winning weight is well, it took a while to my understanding. If I look at previous published papers, standardized, but they are quite close between countries. And that's actually also why Interbeef, I think it's one of the roles of international organizations, try to exchange information how to model a specific trait. But of course, if you look at other traits we are trying to implement, like carcass traits or fertility traits, there is always a research phase behind where we are trying to understand and improve the models before fitting them into the international evaluations. The risk otherwise is that, the genetic correlations will go maybe a bit all over the place, or even out of parameter space. And then it becomes a bit more difficult also to understand what that correlation means. Because when we estimate the genetic correlation, it's not only the G by E that's lowering the correlation from 1 and making it lower than 1. It's going to be also indeed differences in trait and model definitions. So harmonization of trait would really help. Yeah, I agree.
Yeah. Thank you. Sorry, my internet dropped out for a few seconds, so I missed parts of your answer, but I will just watch the video later and then hopefully see it. And sorry, so there are no further questions in the chat, so I have one last, I think.
Can I also ask a question? Sorry.
So, no, of course.
Hey, Renzo, nice to see you.
Nice to see you.
We used to be colleagues in Wageningen, and congrats on the lots of work you've accomplished, during your PhD. I just wonder, based on your learnings from your PhD, what would be like your general advice about beef breeding in Europe to, the beef breeding companies?
Yeah, I think we need to push a bit on genomic. I think I think that will be my biggest piece of advice, because there is a lot of opportunities we are not we are just starting to scrape. And that's maybe the interesting part of my research. Was the most exciting part was in this single step model. But if you think about with genomic data, we can do extra stuff. So for instance, I had a master student working with genomic data and estimation of genetic correlations using genomic data. And this issue with connectedness could be potentially improved using genomic data, because you have disconnected populations that then become connected using a G matrix, for instance. There is a lot to do. And I think investing in genotypes is actually a good strategy. And definitely, I think during the PhD, I got the impression that international evaluations are really, really beneficial. So that's another piece of suggestion. So try to be involved.
Thanks for that.
Thank you. Yeah, I think I leave it with this because it's a nice last answer, or nice last topic. Yeah. So thank you again, Renzo, for the nice talk, and for everyone attending today. And the next seminar is scheduled in 2 weeks. We will have Konrad from the Ross Institute giving a talk. And that's it for today, and enjoy the rest of your afternoon.
Okay. Thank you very much, and thanks for having me.
Bye.
Bye.
I just want to say that we're really proud to be able to continue.
Oops.